Section 7.4, Inverse Laplace Transforms, Part 1. Before now, we were given a function little f of t in the t domain, and we wanted to find its Laplace transform big F of s in the s domain. In this section, we want to do the opposite, where if we're given big F of s, we want to find little f of t. So let's look at an example. So suppose big F of s is 1 over s minus 3. We want to find little f of t. In other words, we want to find a function, little f of t, such that when we take its Laplace transform, the answer will be 1 over s minus 3. So if we look at our table, we know that the Laplace transform of e to the at is 1 over s minus a. So if we play the game backwards, reading this from right to left instead of from left to right, then we see that if we take little f of t to be e to the 3t, we would get a 1 over s minus 3. And so the little f of t that goes with big F of s is 1 over s minus 3 is e to the 3t. So if you think of this forward process as taking the Laplace transform, what we're talking about now is the inverse process when we call this the inverse Laplace transform, and we denote this by L inverse. So let's give a definition. Given a function big F of s, if there is a continuous little f of t on the interval from 0 to infinity, such that when you take the Laplace transform of little f of t, you get big F of s, then we call little f of t the inverse Laplace transform of big F of s, and we write inverse Laplace transform of big F of s is little f of t. Let's look at an example. So if you have the inverse Laplace transform of 2 over s squared plus 4, we could rewrite this. This is reminiscent of something that's familiar to us in our table, I hope, which is we know the Laplace transform of sine 2t. Remember, the Laplace transform of sine bt is b over s squared plus b squared. So we need these to match, this to be a b and this to be a b. If we write the 4 as 2 squared, they do match. And so we see that if you take the Laplace transform of sine 2t, you do get 2 over s squared plus 4. So it must be that the inverse Laplace transform of 2 over s squared plus 4 is sine 2t. So some properties that the inverse Laplace transform has is it does enjoy the linearity property, just like the forward transform did. So the inverse Laplace transform of f plus g is the inverse Laplace transform of f plus the inverse Laplace transform of g. Similarly for subtraction. And so you can break inverse Laplace transforms up over addition and subtraction, and you can factor out constants. So this is going to be very helpful to us, a useful property, and the same one that the forward Laplace transform enjoyed. So for the next example, what happens when you go to play the game, but the function big F doesn't exactly match something that's in your table? And so it requires just a little bit more work. So for example, look at the inverse Laplace transform of 1 over s cubed. Now we know from our table that if you take the Laplace transform of t to the n, you get n factorial over s to the n plus 1. So when our n is 2, you get 2 factorial over s cubed. 2 factorial is just 2. And so this is very, very close. This function is very, very close to this function, but notice that they don't exactly match. The inverse Laplace transform of 1 over s cubed is not t squared. So the inverse Laplace transform of 2 over s cubed would be t squared. So when things don't exactly match what's in the right-hand column of your table, you need to manufacture things or try to make things match. And so we would really like there to be a 2 here so that it would match. We can put a 2 here and offset it using linearity. We can offset it with a 1/2 on the outside. And now this inverse Laplace transform, we just go from here to here, from right to left. We know the inverse Laplace transform of 2 over s cubed is t squared. So this is a t squared, but we do have to have the 1/2 that we had from before that we needed to make it match our template. Let's look at another. If you take the inverse Laplace transform of this quite complicated looking function, 3s plus 2 over s squared plus 7s plus 10, this does not look familiar to anything in our table if you look at it. But if we do a little algebraic manipulation, we can massage it into a form that is something that's familiar to us in our table. So let's use just a little algebra or something that you saw in calculus. We can rewrite 3s plus 2 over s squared plus 7s plus 10. We can factor the denominator. And now doing a partial fraction decomposition that you learned either in algebra or in calculus, we can rewrite this as some constant over s plus 5 plus some constant over s plus 2. We learned how before to find in calculus or algebra how to find those constants a and b that makes this true. But if you just think about whatever the numbers are that make them true, we'll talk about that in just a second. Whatever the numbers are that make them true, watch how we can use this to our advantage in calculating an inverse Laplace transform. Okay? Well, let's go ahead and calculate the constants, and then we'll do the inverse Laplace transform. So to find these constants, I'm going to look at this part. And when I look at this part, I'm going to multiply through by the common denominator. When I do, it cancels here to get a 3s plus 2. When I multiply by the common denominator here, the s plus 5s cancel, and I get an a times an s plus 2. When I multiply by the common denominator, the s plus 2s cancel, and I get a b times an s plus 5. We prefer this form over this form because the fractions are gone. And now there's a variety of ways that you can proceed. I'll show you one way here is that we can expand this out. We can collect all of our s terms together, collect all of our constant terms together. And if you rewrite this as 3s plus 2 equals an a plus b times s plus a 2a plus 5b, then if you look at this here, if this linear function of s equals this linear function of s, then the only way that can happen is if the coefficients of like terms are equal. So that means the coefficient on the s term here must match the coefficient of the s term here. So it must be that a plus b is 3, and it must be that the constant term here matches the constant term here. So 2a plus 5b must equal 2. Now you could solve this by whatever method you like. This is a 2x2 linear system. You could use substitution or elimination, or even use a little baby 2x2 matrix to do this. It doesn't matter. However, here I've shown you the work for doing this by elimination. At the end of the day, a comes out to be 13/3, and b comes out to be -4/3. And all we've done is a bunch of algebra. But let's show how that can be helpful to us in calculating an inverse Laplace transform. So track with me here on the logic. If this function is the same as this function, and it can be broken down into these two functions, the sum of these two functions, and now we know the a value and we know the b value, then that means we can rewrite our original function as this, using our a and our b. And so the inverse Laplace transform of our original function is the same as the inverse Laplace transform of this new formulation. But then by linearity, inverse Laplace transform of this difference is I can just break this up over the subtraction. I can factor out the constants. And now this is something that's in my table. This is just the inverse Laplace transform of 1 over s plus 5. Think of this as s minus a minus 5. The inverse Laplace transform of 1 over s minus a is e to the at. My a here just happens to be minus 5. Similarly, if I write this as 1 over s minus a minus 2, I can do the same inverse Laplace transform and get e to the minus 2t. So notice we used partial fractions and some algebra to rewrite a complicated form into a decomposition of simpler forms which were easier to attack with inverse Laplace transforms. This is exactly what you did in calculus 2 when you wanted to integrate something like this. You split it into a partial fraction decomposition, and the idea is that integrating this complicated thing is being replaced by integrating two simpler things. So the same idea is taking place here. Partial fractions is a very useful tool to aid in computing inverse Laplace transforms. So let's just give you a quick overview of partial fraction decomposition. I'm not pretending like this is completely teaching this to you brand new. Hopefully it's just reminding you of what you did in calculus 2. So the setting for a partial fraction decomposition is you have to have a rational function whose degree, we'll call it p of s over q of s, whose degree of the numerator has to be less than the degree of the denominator. Remember, the degree of a polynomial is just the highest power that appears in the polynomial. So case 1 is what happens when you have q has distinct linear factors. The denominator here has distinct linear factors. You probably remember that the idea is to split this into terms that involve each one of those factors, and then everybody gets their own numerator. And now it's a matter of I need to find the constants a, b, and c that make this true. So just like before, I'm going to multiply both sides by the common denominator. After the cancellation, this is what you get. And in the last method, in the last example when I did this, the method that I used was called equating coefficients, and what we did is we expanded all of our terms. We gathered our like terms, and then we equated coefficients. That's totally fine, perfectly legitimate. Here's an alternate approach that's commonly used in engineering. Sometimes it's called the cover-up method, and I'll explain why. or it's called the value substitution method. The logic here is if this function of s has to equal this function of s, then it has to equal it for all values of s. So that means I can pick whatever value of s I want to and plug it in everywhere I see an s, and I must get a logically true statement. So if I pick certain values of s, it's going to make my life very, very easy. For example, looking at this, if I pick an s of -2, it's going to cancel out this factor and hence cancel out this entire term, and it'll do so to this term also. It'll make 2 of my 3 terms go away, and this is why in engineering they call it the cover-up method. If you pick s to be -2, it's going to make this term vanish, or you could cover it up with your hand, it's gone. And it's going to make this term vanish, cover it up with your hand, it's gone. And we get very straightforwardly, if s is -2, this becomes a -15. This term is a 0, and this term is a 0. So we just get b times a -2 plus 1, which is -1, and -2 minus 3, which is -5. And almost for free, we get 5b equals -15, or b is -3. Very quickly, we were able to determine the value of one of our constants. If we play that same game again, we just want to cover up another term. So I can see if I pick s to be 3, then here I just get a 7 times 3 minus 1, which is 20. This is going to zero out or cover up. This is going to zero out or cover up. And then here I'm going to get a c times a 3 plus 1 times a 3 plus 2. So I get that 20c equals 20, or c equals 1. Now we know we're going to have to make, we have 3 constants. We're going to have to make 3 choices. We've made 2 of our 3 choices, and we have one more nice choice to go. You could pick s to be -1, and there's nothing wrong with picking s to be -1. I chose to pick something different just to show you that you don't have to pick. In fact, if I was doing this, you don't have to pick the values that cover up. You can pick any values you want to. Now, if I was doing this in real life in this example, I would pick s to be -1. It makes one of my terms cover up, but I just want to show you that you don't have to pick the cover up value substitution. So if we pick s to be 0 here, it's often a very convenient value to plug in. Here we get a -1. Here we get an a times a 2 times a -3. Here we already know that our b is -3. We get a 1 times a -3. We already know the value of our c is 1, and here we get a 1 and a 2. Notice that very quickly tells us that -6a is -12, so a is 2. I think this is a more efficient, quicker way to find these coefficients, but you use whichever method resonates best with you. I think it's very effective. So going back, we said that this function can now be decomposed into this function, or these 3 functions, and we know the value of a, b, and c, so let's put them in, a, b, and c. And so by linearity, the inverse Laplace transform of our original function is the sum of the inverse Laplace transforms of the pieces. This is, once we factor the 2 out, is in our table. The inverse Laplace transform is e to the -t. This, when we factor out the -3, is again in our table, and this is already in our table. So again, partial fraction decomposition led us to take a complicated function that we needed to inverse Laplace transform, decompose it into simpler parts, inverse transform the pieces to get our answer to the inverse transform that we originally sought. And let's look at an example for case 2 when the denominator q has repeated linear factors. So a repeated linear factor would look something like this. This is a distinct linear because it is not repeated. We don't see it occur in the factorization except for 1 time. Here this occurs in the factorization twice. The number of times that this occurs in the factorization is called the multiplicity. So this is a repeated linear factor of multiplicity 2. So our partial fraction decomposition theory says that when you have a distinct linear factor, it does what we did before. When you have a repeated linear factor, then what happens is you count up on the powers of your repeated linear factor until they're exhausted. So if this had been a 3, we would have had an s minus 1, an s minus 1 quantity squared, and an s minus 1 quantity cubed. And everyone gets a constant as their numerator. Now you can run the same process that we did before, multiply through by the common denominator, pick your values to substitute. That will quickly lead you to your a, your c, and your b, your a, your b, and your c. And so now we know here in black that this function has a partial fraction decomposition in black of what you see in black. We found the values for a, b, and c. So the inverse Laplace transform of this must be the inverse Laplace transform of this. We'll break up the inverse Laplace transform over the addition and subtraction. We'll factor out our constants. A was 2, B was 3, C was -1. And now every one of these is in our, well, this is in our table, and this is in our table, and this one isn't quite in our table. But we can use the knowledge of what's in our table to calculate this inverse Laplace transform. So notice, if we covered up what's here in green, if we just covered up this and we didn't look at the -1, this is a 1 over s squared. And so this is a shifted version of the function 1 over s squared, and it's shifted by 1. So if you cover up this shift and you think of this big F of s as 1 over s squared, then the shifted version, big F of s minus 1, is 1 over s minus 1 squared. And now if you use our shift theorems from before, but you're playing the game backwards, I know that big F of s has an inverse transform of just t. Big F of s equals 1 over s squared, inverse transforms back to t. And now my shift theorem says that the inverse Laplace transform of the shifted big F must be my original f multiplied by my exponential. Here my a is 1. So that tells us how to calculate this new inverse Laplace transform using our translation in the S domain theorem, sort of read backwards to make it an inverse Laplace transform theorem. So this inverse transforms back to 3 from here, and then t e to the t from what we did right here. One last example type that you might see in the homework that you're tempted to do a partial fraction decomposition on, but it is not a partial fraction decomposition, is something like this. When you have 1 over s squared plus 4s plus 8, so this is a irreducible quadratic. This does not factor over the reals. You can always tell because its discriminant is negative, which you can check. And there's no other terms here, so it doesn't make sense to do a partial fraction decomposition because there's not more than one factor here. So the idea is to reach into your algebra bag for a different trick. Here we just want to take this denominator, s squared plus 4s plus 8, and you will see these in the homework. You need to complete the square. So you can think about this different ways. The way that I think about it is I want to rewrite this as s squared plus 4s plus whatever the magic number is that completes the square, plus my 8. It turns out that when you have a leading coefficient of 1, the way you know how to complete the square is you take the coefficient of this term, you half it, and you square the result. And so that's the number that you put here, and if I put a 4 here, I have to offset it by subtracting off the 4 here. This is a perfect square trinomial. It will always factor into s, this sign, and the square root of this number, quantity squared. And this just is what it is. In this case, it comes out to be a 4. And now I can rewrite this as a sum of squares, and I get s plus 2 quantity squared plus 2 squared. And so the idea is I've taken this function, this rational function, and I've rewritten it in this sum of squares, 1 over sum of squares formulation. And this is more amenable to inverse Laplace transforming than this is. Of course, they're algebraically equivalent, but this is just easier to work with in a Laplace transform context. So if this function is equal to this function, then the inverse Laplace transform of this function must equal the inverse Laplace transform of this function. Now, if you stare at this, and this takes a little practice, I want to be honest with you, you're sort of looking at your table and it doesn't exactly match anything in your table. The first thing I want to encourage you to do when you see a shift, I want you to just cover up the shift. So I want to cover this up and think of this as a 1 over s squared plus 2 squared. Even if the shift were gone, it doesn't exactly match anything in our table because our table would have a b over s squared plus b squared. And if my b here is 2, then I need to have a b of 2 here in order to be able to use my table. So even if we disregard the shift for right now, it doesn't match what's in our table. So let's inch closer to making it match something in our table. If my b is 2 here, I want to put a 2 here, which I can do as long as I offset it using linearity by putting a 1/2 out front. And now if you look at the blue version and you cover up the shift, well, if we write this s plus 2 as an s minus a minus 2, but for now, let's just cover up this shift right here completely. If we were to cover this up completely, and we looked at this as a 1/2 inverse Laplace transform of 2 over s squared plus 2 squared, it looks like the inverse Laplace transform of something like this. It seems like it would inverse transform back to a sine of 2t. And you're correct. So I look at this as what we do have when I remove this shading here, that what we have is a shifted version of something that inverse transforms back to sine 2t. And the shift here is it's a shift up by -2, and now we go back to our theory. Our theory said that if you have a shift in the S domain, that corresponds to multiplication by e to the at. If you have a shift of a in the S domain, then it corresponds to multiplication by e to the at in the t domain. So what I want to do is cover up the shift. I want to mentally inverse transform. So if I mentally inverse transform the unshifted version, think the unshifted big F of S is this, which I rewrote as this. I know that this inverse transforms back to a sine 2t. So that's what the unshifted version would do. So that means the shifted version must take the unshifted version and multiply it by the appropriate exponential. So since my shift was a -2, I want to take the Laplace transform, the inverse Laplace transform of the unshifted version, and I want to multiply by an exponential in the t domain. So you probably have to work through that, think back through that kind of carefully, and we'll see that we cover up the shift, we invert, and then we account for the shift using one of our theorems by multiplying by e to the -2t in the t domain. So at the end of the day, the inverse Laplace transform of this is this function. Practice this in the homework and let me know if you have any questions.